Hi and welcome to another MoTeC webinar. My name's Pete Swinney and today is part 3 of our introduction to M1 diesel tuning. We've got a lot of topics to cover today and some big subjects, so we'll get through as quickly as we can, but it's going to take a while. So we're going to talk about injector timing and the relationship to cylinder pressure, the diesel fuel model itself, so all the tables, or the majority of the tables that you fill out to control the amount of fuel and how they relate to one another. And after the decision for the fueling has been made by the ECU, how to identify, where the fuel values or those limitations for the fueling are coming from. And then finally, injector calibrations. Previous webinars we've talked about some of the limitations of accurate injector calibration, so we'll just go into that a little bit more today as well. Alright, so we're going to start by showing you a cylinder pressure trace. It's quite common for some of the higher end diesel tuners to use cylinder pressure analysis for tuning. Not something the majority get to do in the petrol world other than OEM manufacturers. But it's useful to understand what's happening in the combustion chamber with diesel to help you transition from petrol style tuning to diesel style tuning. So these traces we've got, they're not real cylinder pressure traces, they're just indications of what it might look like, and that they're more about trying to make it easy to draw and for you to see and understand. So for a cylinder pressure analysis, the resulting graph is usually plotted against engine crankshaft degrees, which we have along here on the horizontal axis, and then pressure up on the vertical axis. And it normally rotates around top dead center. That's what we want to see, where the pressure is occurring, how much the pressure is in relation to top dead center. So the first trace we've got here, the black line you see here, is what you might expect from when the engine is cranking with no fire inside. So no fuel added, no combustion, so that's just our flat line of the cranking cylinder pressure. Now we've got some fuel being added, so we'll just go through what's in front of you now. So the blue area here, that's the time that the fuel, or this is the time the fuel is flowing from the injector. So in this case it begins, our injection time starts at 10 degrees before top dead center, and it's finishing something like 7 degrees before top dead center. Alright, and then we've got the sort of mustard color here, that's our delay to combustion. So despite the fact that all the fuel is in the cylinder, it's not actually starting to burn yet. So we have a definite amount of time after the fuel is stopped and before we get our flame starting to occur. And again, this is just a representation to help you understand what's going on in there. And then obviously our red area here is our combustion time. Now the thing to remember about a diesel compared to a petrol is that the tiny droplets of fuel, the mist of fuel, is going in, and rather than like a sweeping propagation of the flame that you get in a petrol when you light it in one location with the spark, a diesel tends to get thousands of little flame fronts for each droplet. So say 60 or 70%, could even be higher, I don't know exactly, amount of the fuel actually all burns at once. So each droplet becomes its own little combustion area, I suppose. So it makes a very fast chain reaction. So if anything doesn't instantly self-combust at that first moment when all the droplets get hot enough, then it certainly it combusts very quickly as a result of all the existing burning droplets of fuel. So long story short, you get a very large and very quick pressure rise because of all of this fuel almost burning all at once. And so that's represented here. We have a blue line showing that pressure increase, and This is a sharper than normal pressure increase, certainly compared to a petrol engine. So we get all the fuel burning off very quickly, so we get a very sharp pressure rise here, and that sharp pressure rise is the diesel knocking noise that you can hear on an older style diesel. So that's a diesel without a pilot pulse. Now, as you guys get into doing some tuning of your own, you'll be able to turn pilots on and off and just hear the difference between running with and without a pilot and how much noisier the combustion gets. Alright, so I think that's pretty much covered that. Alright, one last thing. In reality, not that you probably know, but in reality, when you're doing cylinder pressure analysis and tuning via that method, you're actually trying to get the 50% burn point or the 50% heat release point to a specific location in the cycle. It's normally around 10 degrees after top dead center. Now, most of you will be doing your tuning on a dyno, so you will end up moving your injector timing around until you get peak torque, just the same as you would with a petrol engine. So initially, we move our injector timing around at low loads to get peak torque at the dyno, and that will, in fact, if you were to measure it with cylinder pressure analysis equipment, probably have that 50% burn point around the 10 degree after top dead center point. All right, so that's what's going on at that with that heat release location point. We're aiming to get that around that 10 degrees after top dead center. Alright, so in this case we have one pulse being used, and I think you by this point in the webinars understand that we have 4 available pulses in a diesel ECU, and so this is the pulse width number 3 is the main pulse, which is the intended pulse for delivering the most amount of power. You know, the bulk of the fuel should come from that third main pulse. Doesn't have to, but that's, you know, basically we label it as the main pulse, and the first 2 pulses are designed to be used for pilots. Alright, now the thing to note about this and to get your head around is that we, unlike a petrol, we can't start delivering the fuel with our diesel until we get to the injection timing point, the beginning of fuel delivery. So our beginning of injection in this case is starting at 10 degrees. Now on a petrol engine we get up until 10 degrees potentially to deliver our fuel. We can actually be delivering fuel on a petrol engine for 720 degrees. So it's with a diesel engine we only get a very small amount of time to deliver fuel. So time and crank degrees become quite critical for understanding where you should be delivering the fuel and when to start that fuel delivery. So I just wanted to show you here that at 1000 RPM, which is just above idle, 6 degrees of crankshaft takes 1 millisecond. So a 1 millisecond pulse means the fuel is squirting over 6 degrees of crankshaft. So if we are trying, for example, to deliver a 2 millisecond pulse, that would be still squirting fuel in 12 degrees. So if you look at that with our example there now, if we had a 2 millisecond pulse and we started at 10 degrees before top dead center, that will be 12 degrees, so fuel would still be squirting in after top dead center, then there'd be a delay and then the combustion would start. And that mightn't be too bad, but if you take that same amount of fuel and you inject it at 3000 revs, so 1 millisecond at 3000 revs lasts for 18 crankshaft degrees. So what that would mean is that's right, at 18. So for 2 milliseconds that will be 36 degrees of crankshaft before the fuel was all in the cylinder. So if you can, I'm sure you've done the maths in your head. So if we started at 10 degrees before top dead center and we went for 36, that's 26 after top dead center. That's way over here before we've stopped injecting fuel. We then have our approximate half millisecond of delay and then the combustion would start. So that you can see already that that would be way too late. So having long pulse widths in diesels is not ideal. And to give you some idea, the average 3-litre common rail diesel engine that we've been working on, the maximum pulse width at their standard power levels is something like 1.8 to 2 milliseconds. So as you can tell, if we're going to run a long pulse width, somewhere around 2 milliseconds, we're going to require to advance the injection timing to make sure we're not squirting fuel while the piston's going down the bore. So as the pulse width gets longer, as we add more fuel and the pulse width gets longer, we need to add more timing. So this is actually kind of almost the opposite of petrol, where your injection timing numbers go up as your pulse width goes up. Now fortunately, if we want to add fuel in a diesel, we don't have, well, we have two options. We can increase fuel pressure to increase fuel flow. So rather than increasing our pulse width, we can actually increase our fuel pressure enormously from idle. So we could have an idle fuel pressure of something like 40 MPa, but we could potentially lift that to 220 MPa. So that's significantly higher. So we don't have to, and in a lot of cases don't want to, run any more pulse width than say 1 to 1.5 milliseconds. Alright, so just what I wanted you to understand out of all of this, and we'll talk about it in later and in other webinars, is that adding pulse width, so adding more fuel via making the pulse width longer, effectively retards this ideal 50% burn point. It retards your combustion pressure curve. So that is just not the case with the petrol. If you make your petrol engine richer, make the pulse width longer in a petrol, it doesn't affect the point at which you would light the ignition or light the fuel. The only thing that changes the decision on your ignition point is more the load or the boost, and it's not about how long the pulse width is. So when you make the pulse width longer in a diesel engine, you need to probably consider that you're going to be adding injection timing. The start point gets earlier, or should be earlier. Alright, so just a basic overview of that for now. Alright, so second trace here, it's now the purple line, and we've added the pilot. So I just wanted you to see what a pilot would look like, where it's kind of located. And so we can see that in this case we've added or utilized our first pulse width, pilot number 1. There it is there. So the fuel is flowing, starting somewhere around 24 degrees and finishing at about 22. So very small pulse here, or a small amount of flow, and then a similar delay time, and then your combustion time. So the idea of the pilot is just to do a little preheating amount in the combustion chamber, and its purpose mainly is to soften this pressure curve, this pressure rise, and take it from a really sharp pressure rise and kind of lead a softer increase in fuel or that combustion burn. It has the net effect of just quietening down the noise from the engine, and for racing, realistically, you don't need it. We haven't been able to prove that it does make more or less power. It certainly, pilots 1 and 2 help with cold start and cold running, because they effectively are like a little miniature glow plug. They just put this little tiny flame in there and then heat up the combustion chamber and allow the main lot of fuel to light easier, and you get a better combustion burn in that case. But as far as power goes, I can't really say one way or the other at this point. So I know most performance teams are not using pilots, so it's more of a drivability, definitely helps for reducing emissions and reducing combustion noise for customer satisfaction. So that's the idea of the pilot, and that's what it looks like. Now Certainly modern vehicles run two pilots to help get that noise even lower and to help the starting and cold running. So one more thing to note coming up here: if you are positioning your pilots, our ECU allows you to not only define the volume of fuel, the mass of fuel for the pilot, and also you can also move where that pilot occurs in the cycle, and you can move that in relation to the main, so you can define that it stays a set amount away from the main, let's say 20 degrees or 15 degrees always away from the main timing, or you can have your own three-dimensional timing for your individual pilot. So you can have a 3D injection timing for your pilot 1, a 3D injection timing map for your pilot 2, and a 3D injection timing map for your main. Just while we've got the fourth pulse width here, the post pulse width on the screen, the intention of this pulse width, or this amount of fuel, is that is used after the main combustion has been completed. So it's not a power delivery fuel amount, and that was in our last webinar where we showed you that the post is not used as part of the main fuel calculation. So if the ECU looks through all the limiting tables and the pedal request and comes up with a fuel delivery of, say, 50 milligrams of fuel, that has the possibility of being divided out amongst the first three pulses. The fourth pulse, the post pulse, that has its own individual calibration, so you can add defined amounts of fuel at defined times after top dead center to do things like make boost, so for anti-lag, and for doing things like heating up diesel particulate filters for burning off the deposits in them. So the three first pulses are for delivering the calculated fuel for making the power, and the fourth pulse is for boost, enhancement, and emissions. Alright, so now this is a bit of a flow chart of the fuel model, and what I'd suggest is that this you almost might be worth printing this out and putting this on your laptop so you can keep a track of what's happening. You're always, as you start tuning, looking at why perhaps the fueling isn't what you thought it would be, and where the current fuel numbers are being derived from. So it's not like a single fuel map that you get in a petrol engine. Petrol engine's actually relatively simple compared to the possibilities of where the fuel is being calculated as coming from in the diesel packages. So what I'm going to do is start on the right hand side of the screen here, and at what I believe is the start of the calculation. So we define this a table. It's actually only a 2D table, and we'll show you what that looks like in a few slides, of what the fuel mass limit is. So this table is called the fuel mass limit main, and what this means is no matter what happens anywhere in the calculations, anywhere in the ECU, that you will never ever get any more than the number in this table. So this is the maximum amount of fuel mass that will ever be delivered, and that can only ever happen if all of these other tables don't have a smaller number in them. So we start by setting that number, and this is based on engine speed. So it's a simple 2D table that says at any given engine speed, this is the maximum amount of fuel that we want to deliver to this engine. That is then scaled, that fuel amount. So let's pick a number and call it 100, which isn't 100, and that's in milligrams, by the way. So 100 milligrams isn't a mile away of what might be a common number to put in there. And so that 100 milligrams is then scaled by the fuel mass nominal table, which, if you can think of it at this point, basically as the throttle pedal. So if that fuel mass nominal table just had a linear representation in it, as in zero pedal is 0% and 100% pedal is 100%. What that would then do is basically scale that fuel mass limit number between 0 and 100. Now I probably should have gone to the fuel mass minimum before I said that, but the minimum fuel mass is also derived down to be the minimum amount of fuel at the bottom. So the pedal actually scales between 0% pedal would be the fuel mass minimum, which is the fuel mass that's used to keep the engine running. So at idle, overrun, that is the intended amount of fuel to overcome the friction of the engine to keep it running. Okay, so the fuel mass minimum is the minimum for the engine to run, and the fuel mass limit is the maximum amount of power you ever want to make, because in a diesel, power is pretty much proportional to the fuel that's put in there. Alright, so this is the maximum amount of power you want, the minimum amount of power that you want, and your throttle pedal simply runs up and down that scale. So 50% pedal would mean halfway between our minimum fuel mass, which might be, let's say, 5 milligrams, and our maximum, and if we make the number easier and call it 105, well, it's something like 50. Alright, so that gives us a channel which the ECU uses, and that channel is called fuel mass unlimited. So that is the beginning of what is going to end up being delivered to the injectors. It's the beginning of the calculation. Now that heads off down to our fuel mass, our final fuel mass that's going to be delivered to the injectors. Now you can actually, as simple as configure these two tables, the throttle pedal table, and drive that engine straight away. If it's a bit smoky, you take your foot off and it won't be so smoky. It literally you can virtually start it with some basic configurations and drive it straight away, and as long as you regulate the amount of fuel with your pedal to make sure you don't get too rich, you can drive it around the block within 2 minutes of configuring it. Now if you make the number in this table too big and you put your foot down and there's not enough air in there, air in the cylinder, the boost is very low, and you apply too much fuel, you'll fill the street with smoke. And that might be okay for some of you, but the majority, and certainly parts of the world where we live, the majority of people want to try and reduce or minimize the amount of smoke. But other than that, you won't have a problem. If the engine's set up and running okay mechanically, and you've got your ref sync mode and everything right, and your injector set up right, so the injectors are being driven correctly, so the fuel tuning can be as simple as just those three tables and you're on your way. It's not like a petrol where you have to get the air fuel ratio at one particular level. That engine will run and idle at lambda 10, it'll run down the road at lambda 5, lambda 3, lambda 2, lambda 1, and it'll even run at lambda 0.6. It'll just be smoking. But either way, the power will be, or the fuel will be proportional to the pedal, and it's as simple as that. So, and it would drive like that provided all the tables on this left hand side all had numbers higher than our example of 105. So if all of these numbers and all of these tables here had, say, a milligram number of 300 in them, then the fuel system would just use the result of this very simple fuel calculation here. Now, of course, that's not the reality. In most cases, you'll be fitting an M1 to a diesel engine so that you can make maximum power, and in a lot of cases you want to make maximum power at minimum smoke. And again, I know that's not all cases, but this package is aimed at allowing you to get very, very accurate fueling. So we want the maximum fuel to be delivered to the engine at all times without creating smoke. So we have tables to allow us to do that task. Alright, so Clearly, this method on the right, where we're just deriving fuel based on pedal and nothing else, we're not going to get much control of smoke, and so we need something else. So we have on the left hand side then our fuel mass limit tables. So this is a range of tables that allows you to pull or to restrict fuel for when there are issues or smoke limiting, or for whatever reason that we've pre-thought that you're going to need to remove fuel. So it's kind of split into two aspects: safety and smoke. So the first two tables are to do with smoke, and so we'll start at the top. And these ones with the asterisks by them, they're the ones that you're commonly using, and are the ones that are commonly what I would call in play. So we'll just go down these tables and give you a quick explanation of what they are intended to do. So our first one here is our smoke table, nicely named. And what this table is a two-axis table that gives you mass airflow on the vertical channel, vertical axis, and engine speed on the horizontal. So basically the amount of air going into the cylinder, and you get to define or limit the amount of fuel at each location. So I might just hop forward here and show you what that looks like. Alright, so here's our smoke table, and see we have engine charge limited, engine charge unlimited. So this is basically our airflow meter on the vertical axis, or if that's not working, our engine efficiency table, calculating the amount of air going into the cylinder. And remember, in a previous webinar we explained what that was represented as, and that is in milligrams or weight of air. So on this vertical axis here, we can see we've got 2,000 to 2,400 milligrams of air. These are real numbers. This was from an Isuzu, I believe, Isuzu 3-liter. So this is how much weight of air is going into each combustion event, into each cylinder. And so what we can do is we can see at any particular airflow or any particular air engine charge amount, we can limit the amount of fuel. So the number in here is milligrams. Have a look up the top. Fuel mass limit smoke, milligrams. So these numbers are milligrams. So I could have my foot flat, so my pedal at 100%, which would mean, if we go with our example, 105 milligrams. But if I was at this intersection point, which is 1750 revs here and 2100 milligrams of air, that I would only get 68 milligrams, or this table would output 68 milligrams. So that is despite the fact that we're asking for 105 milligrams, this table will limit us to 68. So we'll go back now to our fuel flow chart. Alright, so our smoke table gives us the ability for any given, and I'll say airflow, but it's actually in air mass being entered into the chamber. For any given air mass, we can limit the amount of fuel going in. And that smoke table actually has a driver input smoke trim on it as well. So you can put a 9-position switch on your dash and dial the smoke table in and out as a compensation. So at this point I might just point out that what we're heading towards here with all of these limit tables is the ECU running through all of these tables and looking for the lowest number. So between 1 and 200 times a second, it's checking on all of these tables, choosing the lowest number, the lowest fuel mass. It gets spat out and becomes the fuel mass limit. So this channel here is the fuel mass limit channel, and it is the lowest number from all of these tables. That fuel mass limit number is then compared to the fuel mass unlimited number, and the lowest of those two becomes the actual requested fuel for the engine. All right, and then that fuel for the engine gets divided over as many pulses, as many of these 3 pulses as you want. So you can divide it over 2 pilot pulses and then the rest can be the main, or you can have it all in the main. Alright, so the intention is that for any given fuel mass request is that no matter how you choose to divide it up, it will always be the same amount at the end. So if this number becomes 68 milligrams, then you should be able to either have 68 milligrams in the main, or if we decide to divide it by 20%, you want 20% in pilot 1, then it will automatically part off 20% of the 68 and allow you to run the pilot and still deliver exactly the right amount of fuel so that it's still 68 milligrams. And ideally, and we'll know that that's right because if you pull the pilot in and out, if you were to turn the pilot in and out, the engine power shouldn't change. Alright, so that's our ideal aim that we're trying to achieve, is to be able to take that fuel mass and deliver it out via any combination of these 3 pulses that we want. Alright, so that fuel mass is derived from the fuel mass channel, and that fuel mass channel is derived from either the fuel mass unlimited or any one of the fuel mass limit tables, whichever is the lower of the 2. Okay. Alright, so going back to going through the list here, so this smoke table is, as the name suggests, is designed to, if the airflow is low, i.e. the boost is low, and we've got our driver with his foot to the floor and his fuel request is high, and we know that's going to make smoke, you get to tune this table in milligrams to reduce the amount of fuel until the smoke stops, or till you reach the lambda you want. Alright, so that's method 1 for dealing with smoke, or for trying to obtain a particular lambda value, if you like. Now, in racing terms, a fairly typical number to head for that's close to full power with minimum smoke, and I mean it's different for all engines, but a lambda value of around 1.2 would be a good starting point for any engine that you want to start tuning. So if you go forward and just think, I'm going to target lambda 1.2 to be my starting point, in most cases that I've ever struck, that should be virtually no smoke under normal conditions. If there's lots of smoke and your lambda is 1.2, then you've got probably a timing issue or some other issue. So you should be able to be at lambda 1.2, 1.25 and only maybe have a haze of smoke at worst. Alright, so that smoke table allows you to do that tuning using milligram numbers of fuel, using physical, the channel or the unit of measurement being milligrams. Now the fuel mixture minimum table is virtually the identical thing, only you can actually type in your aim lambda, your aim fuel mixture, and provided your injector calibrations are perfect, which is almost impossible, I'm sorry to say, but if they were perfect, then you could simply type in lambda 1.2 and then the system, if all calibrations are correct, it would just know what the airflow was, what the fueling is, and just maintain fueling to suit. And this is by far the most preferable way of controlling your lambda, but for it to work well, you need to aim to get your air mass calculations correct, so that's an accurate airflow meter, and your fuel mass calculations correct, so that's accurate injector calibrations. Alright, does that make sense? I don't need to show you that table. It's still got mass flow or milligrams of airflow, milligrams or the mass, air mass on its vertical axis. But you can, in most cases, normally get away with just a 2D table, which is proportional to engine speed. So just engine speed on the horizontal axis, and put in your lambda aim, and you're away. It'll just, the ECU will automatically limit the amount of fuel based on what it calculates the lambda is going to be. Alright, it actually uses the lambda estimate channel to do that. So that's that channel we explained. If it wasn't last webinar, it was the webinar before. Alright, so that it doesn't use live lambda to do that because that's too delayed. It uses lambda estimate. So your whole, not your whole purpose in life, but it certainly makes your life a lot easier if you can get those injector and air mass flow calculations correct, or calibrations correct, and then you can just enter in the lambda you want to run and it'll just flatline it for you. It really works well. Alright, so they're actually either or both in combination are the two tables that you'll actually do your fuel tuning with. So you could almost think of those as a little bit like the time you spend in your efficiency map with your petrol tuning. You spend that kind of time in one or both of these tables here to get your fueling right for the amount of air that's being delivered. Okay, the next one down, inlet manifold pressure table. This one really is just used in most cases to limit the amount of boost. If you get an overboost situation, then you can just pull out a whole lot of fuel to stop the boost being created. So it's removing fuel is a very nice way of limiting the way the engine makes boost, and you obviously don't have to pull it out all at once like a fuel cut. You can make quite a soft reduction of fuel if you see that fuel pressure, if you see that boost pressure is getting out of control. So we don't use that commonly, but it's there if you want to use that method. You've got a method for changing fuel based on altitude, which again isn't often used, and then we get to our next one, which is the engine speed limit. So this table, or this part of the calculations, is removing fuel quite often. So engine speed limit, every time you come near the engine speed limit, you'll find that it has control of the fuel mass. It becomes the winner. If you run up to the engine speed limit and it's not configured as cut, then the engine speed limit set of tables will take over the fuel mass or become the lowest number, and then that will become the fuel mass that the engine will use. So it will become the lowest number to be used by the main calculation to be delivered out. And I've got some tables to show you that happening at the end of the webinar. Alright, so then we can control fuel mass based on launch, fuel mass based on exhaust temperature. You can imagine that's quite simple. EGT gets too hot, just take fuel out. And I suppose it's good to mention here, completely unlike petrol. When you take fuel out of a diesel, you reduce exhaust temperatures, everything gets safer, it gets leaner, everything cools down and power goes down. Unlike a performance turbo petrol engine, where if we take fuel out, if it's running 0.80 at 3 bar of boost and we start creeping fuel out of it, it'll make more power, the EGT will go up, and it's not what you'd call a safety strategy. So but on a diesel, removing fuel is a safe thing to do. It takes power away, it takes temperature away, and yeah, there's very little downside. Alright, and then any of our faults that occur, so if we have an oil pressure fault, any faults that we choose to, we can have that fault condition actually remove fuel. So we can have 50% of the power reduced if we want, if something goes into error, to tell the customer that there's something wrong, needs to pull over and get it fixed. Alright, now out of all of those fuel masses limits, those fuel mass limits, as I said, they all produce what's called the fuel mass limit channel. And then that final fuel mass limit channel, before it heads off to the main fuel mass calculation, can have any of these tables as compensations. So we can have a coolant temperature compensation, another exhaust temperature compensation, a turbo speed compensation, and a gear compensation. So we can remove power based on any of these at the last minute, no matter which, or at the last part of the calculation, no matter which one of these tables is in control. So the final result of any of these limits has a compensation that can apply to it. Alright, I know there's a lot of fuel mass words in there, and it's probably a little confusing, but hopefully the diagram helps. So just to review, the beginning of the calculation is the driver's pedal request between the limit table and the minimum table. And then if that milligram number that comes out of that calculation is lower than any of the milligram numbers in these tables and compensations, then that is what becomes the fuel mass to be delivered to the engine. And then that fuel mass to be delivered to the engine goes through the injector calibrations and then gets calculated as a pulse width, and then your tuning, your tables of pilots and main then decide over how many pulse widths that fuel mass is being delivered. Alright, that's a big page. Alright, so here's what the tables look like, and hopefully you've got your head a little bit around what I'm referring to as we go through these tables. So I said this was a single axis table. This is the fuel mass limit main. So again, always when we're looking to see what the numbers mean, we look at the unit beside the channel description. So this is a fuel mass limit main, and it's in milligrams. So no matter what, at 1000 RPM, 1000 engine speed here, we can never get more than 40 milligrams out of the system. Alright, so if we were to start to tune this engine and we were going to be very conservative, you could just put 30 milligrams all the way across here and then go drive it. And you'd put your foot to the floor, and it probably might run something like lambda 5, and wouldn't pull the skin off a rice pudding, as they say. So the process is you simply keep adding this number up until it starts to make more and more power, and then once it starts to get to a situation where you're getting too rich, then maybe if you're getting too rich because you're not making boost, you can potentially go away to the boost control system and make some boost. But if you're making the boost you want and you're making the power you want, then that's potentially the limit of the numbers you want to put in here. Alright, so that's our maximum fuel that can ever be required, and then that is scaled by our pedal, which is called the fuel mass nominal. So that is simply throttle pedal on the vertical axis and engine speed on the horizontal. So in this example here, so we're at 500 RPM. It's not a very good real example, so it's probably on the simulator. And so our pedal is at 60%. So we could, maybe this might be the engine's about to stall. Drivers got the pedal at 60%, and you can see that's why this is shaped like this. So we have a number of 30 here and a number of 96.5% here. So that's 96.5% of 30, alright, which would mean we would be delivering, our intention would be to deliver 28 milligrams, 28.95 milligrams of fuel to the engine. Okay, so it's likely that none of the limit tables would have numbers less than that, so that would probably be delivered, and we're trying to obviously get the engine to speed up. Okay, alright, so that's how that works. And as I said, at the bottom end of that scale, or of the pedal, you have the minimum amount of fuel that's going to be delivered. So we've got our total limit at the top, our fuel mass limit at the top of what's possible, and our fuel mass minimum at the bottom. So we've got, in this case, coolant temperature and engine speed. So because if the engine's very, very cold, it'll require more fuel to idle. More fuel is a minimum amount. Now this milligram number, see here, milligrams, fuel mass minimum in milligrams. This number here is the number that you would expect to use to have the engine provide its minimum speed, I suppose, so at idle. So this is the part of the actual idle control system uses this, and you can think of it as the feed forward for the idle. So when the engine comes back down to 800 RPM at idle, at a hot idle, the idle control system uses 3.4 milligrams as the starting point, and then closed loop add or subtracts fuel from that point. So if you know much about idle control systems and PID, it will use integral to, if you saw the idle control system with a 4 milligram integral in the positive, that would simply mean that in reality you should probably come back here and add 4 more milligrams to this spot, because it means that the idle control is correcting this number by 4 milligrams to achieve a normal operating temperature idle. Alright, stepping through the limit tables here. So here's our smoke limit table, which we spoke about. So simply engine charge as calculated using airflow meter or engine efficiency and air temperature. So our engine charge channel with our engine speed channel, and then the numbers in here are milligrams. So if you put a number, if you put the whole table to 0 in any of these tables, then the engine would just idle. All it would do, no matter what you did with the pedal, would be to use this minimum number. It wouldn't do anything else. Alright, so that smoke table, here's our driver trim for that. So we've got 9 position switch here. It's actually 10 if you count all of them. So we've got 10 locations where we can add or subtract, if you like, percentage on these numbers. So see here, percentage trim. So if you're going out tuning for the first time and you're using this table, it's that you could actually put some big numbers and flick backwards and forwards on the switch and add and subtract fuel. But I would just use the laptop, obviously. But yeah, maybe if you're having to tear out on a race and you've just got a driver and he doesn't have a laptop, then this is a way of controlling fuel, but it does only trim the smoke table. Alright, so if the smoke table's got a number of 300 everywhere, then unless you put a massive trim in here, it isn't going to do anything to controlling the fuel. Right, so same function but different method of doing it. This also controls smoke, and this just controls smoke by you actually targeting the lambda you want to run. Alright, so it's the fuel mixture minimum table. And again, it has engine charge on the vertical axis, engine speed on the horizontal, and you simply put in here the lambdas you want to run. Now sometimes if the lambda estimate, which is what the lambda the ECU thinks, which is the lambda the ECU will use in this table, if the lambda estimate is not the same as the actual lambda because of your calibrations, and I know you're getting sick of hearing that, but if it's not the same, you don't have to necessarily calibrate everything to get it perfect, to get those channels lined up. You can simply put the lambda in this table that gets you the result you want. So maybe a lambda of 1.15 at this point here, if we target a lambda 1.15 and our lambda estimate would be 1.15 at this point, but we really want our main measured lambda is 1.2 and we want to aim for 1.2, then we can actually put in the lambda number here that gets the actual lambda result we want. So they could be different. Again, I know too much use of the word lambda in that sentence, but so just you can target different numbers here. Just because they're not the same as what the lambda sense is actually measuring doesn't mean you have to use those numbers. So sometimes these numbers can look a little funny and unusual because your fuel injector calibrations aren't right. Okay, so I would now, after in recent times getting, I would be tending to use this table. It's more consistent, more accurate, and a faster way of doing it, using this table to control your air-fuel ratio, your smoke, etc., rather than the smoke table. But if you understand how both of them work and relate to one another, you can choose. Alright, so here's our inlet manifold pressure table, which, as I say, you don't commonly use. And here's kind of an example of numbers you'd put in here. So if my mass limit table was 120, so I never want any more than 120 milligrams, then I put a larger number than that, then this will never be used. Same with my altitude one, unless I'm running, Dakar and up in the Andes or somewhere really high where I want to reduce power based on altitude, then put a big number in here and the ECU will never use it. Okay. Alright, and these are then the compensations of the final result of those limit tables. So we can obviously remove fuel when we're too cold. We don't want the driver, making too much power potentially when the engine's cold, and we can also remove fuel when we get hot. So here you'll see in this example, if our engine temperature, coolant temperature gets to 130 Celsius, basically we're pulling everything out, so this engine will just idle. Okay, same for exhaust temperature. You can see based on exhaust temperature we're removing significant amount of fuel as it gets hotter and hotter. And same with turbocharger speed. We haven't started talking about turbo speed, but generally with diesel engines we're running turbos right on the limit of exploding, and that is because the more air we can get through our engine, basically the more power we can make. So in an ideal world we'd run our turbo at the maximum speed possible all day long and then just add and subtract fuel to suit. So turbos are a gigantic consideration with diesel tuning. It's a very big topic, and you are constantly looking at boost control and turbo sizing to work in relation with injectors and fueling that you've got. So it is quite common to have turbo speed on the turbocharger, and if you get to a point where you've measured and know that you're at a dangerous turbo speed, you can pull fuel as a result of that. Alright, and then down the bottom there's your gear compensation, so that's pretty straightforward. Alright, so that's the fuel model. The nice part is you can go backwards and keep reviewing those layouts, the flow chart, and those graphs, but that's not everything that affects the fuel, but that's the majority of what you'll be touching as you start your tuning career in this industry. Alright, so as you do start tuning, and often you're looking to see why you may be making either too much or too little power, you're going to want to understand which of all of those tables that we've just covered is the one that's producing that final fuel mass number that the engine is using. So you'll want to know which table to go to modify which one. Why is the engine making no power, and you see the fuel mass at 30 and your foot's flat and your smoke table's alright and you can't understand why there's no fuel going into the engine. So it's very common to use I'm going to show you over the next 3 screens how to find out which table is controlling your fuel mass. So as with the petrol packages, we have this nice feature that shows you the source of things. Where does the engine speed limit source come from? Where is in this case where is the fuel mass source? So we have two source channels, which does get confusing, I'm sorry. So we have and I'll go back actually at this point, and just so you can understand or help to understand what I'm going to talk about, bear with me. So we have the fuel mass source here. Alright, so where is this coming from? Is the current fuel mass being derived from the pedal, which is effectively the fuel mass unlimited, or is it being derived from one of these limit tables? And then our second source channel is, out of all of these limit tables, which one is got the lowest number? Which one is actually feeding the fuel mass limit channel? Okay, so Here we go. So currently the engine is being supplied by the fuel mass source, which is the pedal. So it's coming from the right hand side of our flow chart there. Alright, so that is something you can plot and see as a graph. So here it is captured on the software. And our fuel mass limit source, it's not being used, but currently the lowest table, or sorry, the lowest number in all of those tables, those limit tables, is the smoke. So the smoke, if we move away from the pedal being the lowest number, and we go to, and the limit, one of the limit tables becomes the winner, the lowest or the safest number, then that currently is the smoke table. So two fuel mass or two source channels to look at. Now here we can actually see the milligram values as such of all the different those different tables. We can actually look at them as graphs. So the green one here is the final delivery amount. That's the actual fuel mass. I have to keep moving my mouse to keep it in front of you. Then we've got the fuel mass limit inlet manifold pressure, and you remember that was a big high number. So you can see here that's the blue line. It just stays blue and goes across. Then we have the pink one, which is the fuel mixture minimum. So even though you determine that in lambda numbers, it spits out of that table a milligram amount. So that's our pink line here. Then our light blue line is the one coming from the smoke table, and that's defined definitely in milligrams in the table itself. And then you've got the, no matter what happens, I'm never going to get any more than this, which is the limit, fuel mass limit main. Alright, so the red line is, we'll never get any more fuel than that. So anything that's above the red line is never going to be in play. So that's the inlet manifold pressure. So the things that are in play are the pedal. Alright, so the pedal, which is our fuel mass unlimited, which isn't actually on here. So the pedal up until this point here it's derived, because it's the pedal times the main number is a number lower than any of these other channels, then it's the fuel mass source all the way up into this point here, and at this point is the pedal. It's coming from the throttle pedal, which is our fuel mass unlimited. Alright, so pedal times the main, if we did the maths on all of that, that would be 40.6% of our main at 140 is going to be something, with when you take the minimum off, it's going to be something like whatever the milligram amount is, which is actually covered over by my screen capture. Sorry about that. Anyway, so that's what's happening at that point. So we'll move to the next screen, and at that point we're on a little bit in time. So here we are a bit further down the track, and something's changed. Our fuel mass source now, the stuff that's going to the injectors, the final calculation for the injectors is now smoke. So our source channel has changed now to smoke. Our fuel mass source is coming from that list of limit tables on the left, and the lowest number at the moment is still the smoke table. So the smoke table has now become the main fuel mass channel. Alright, and here you can see, so for this amount of time you can see the the smoke line here is obviously, we've got some lower numbers happening in the table, and so at this point here where my mouse is, it became lower than the calculation of the pedal, and it became the winner. So it now is deriving the fuel mass to the engine. Now as the engine is changing, maybe as the pedal's going up, the engine is changing dynamically, the numbers in the smoke table are changing, and I can see I've actually purposefully for this example put those numbers way up. So as those numbers go higher and higher, then you can see that we're going to make a change. So you can see already what's going to happen here. Our fuel mass, which is the green one, our fuel mass channel, gets to this point here and then follows the new lowest number coming from a new table, which you can see if you trace back is going to be the pink. So we'll go one more screen on, And so now where I've clicked the cursor, our fuel mass source now is fuel mixture minimum, and that's coming from the fuel mass limit table, which is the fuel mixture minimum table. So they're both the same. Takes you a while to get your head around this. Hopefully these few screens will help you understand, and you can come back. So as you can see, this is the output of the fuel mixture minimum table, the pink line, and as that's gone down and the smoke table numbers have gone up, it then becomes the lowest number out of all the numbers in all the tables, and has become the fuel mass source itself. So right now the fuel mass to the engine would be 107 milligrams. Alright, so our limit, oh yes, see, our limit here is 140. Alright, so there's 107 milligrams of fuel being delivered to the engine. Now I know that doesn't do the maths right with the pedal, but our pedal isn't linear. We've got our pedal might be at 45%, but we could have a number of a linearization number of 80 or even 100%. So 45 can equal 80% of the main. So the whole intention of the pedal table, which is called the nominal table, is to allow you to linearize the power, or have the power come on any way you like, proportional to where the driver has the pedal. Alright, so that's what's working out there. Alright, so that's how your fuel mass limit sources can be tracked, and you can see what's going on, and you can see which fuel table is delivering or deriving the fuel that's going to the injectors. Alright, nearly there. Now, one more step. The calculation actually spits out a milligram amount, which we've spoken about, but our injector calibrations, or our injector linearization tables, are still in a volume. So that milligram amount is converted into a volume and then turns up on the horizontal axis of the injector linearization table. So whatever delivery amount is requested, so looking at the capture here, we could say, let's say 38 microliters was requested. We would then look at the fuel pressure, which is 180 or over 180 in this case. Alright, so if it did request 38 microliters out of the injector at 180 MPa, the injector in this case would be energized for 0.52 of a millisecond, which is 520 microseconds. Alright, and again we're just reminding you here that to see that the dead time goes down as the pressure goes up. Alright, so I'm going to suggest perhaps as you learn to tune, you're not going to mess with these tables too much, but once you get your head around and you get comfortable with tuning diesels, you'll start to, unless you get individual calibrations for every injector on every engine, you'll start modifying these injector calibration tables to get your lambda estimate to line up with your lambda actual. Alright, so we really want to stress, if you're going to play with that stuff, is that little numbers, any number you get correct at any one site, numbers above should be going down, numbers below should be going up, and numbers to the right should be larger and numbers to the left should be smaller. Okay, alright, so that's that. And now just a final screen on injector calibrations. So why have I said all webinar that they're hard to get right? And so the reason is, well, one of the more simple to explain reasons is that modern injectors have multiple holes in them, and they do that so that you can have a good fine spray going to all locations of the combustion chamber. And one of your other requirements of diesels is to run extremely high fuel pressures in order to have a very fine mist. That helps combustion start. So if we're going to run very high fuel pressure out multiple holes, yet deliver very small amounts of fuel, then we've got to have very, very small holes. And the holes are so small that on certainly some of the let's say cheaper manufacturers, not necessarily Bosch, but some manufacturers, and this is only my reading of it, struggle to get every single hole on every single injector is exactly the same. So what you get is each individual injector doesn't flow precisely the same amount of fuel for any given pulse width. So what that means is that the process then goes that manufacturers produce the injectors and then individually calibrate them and give them their own code of a linearization table, or it's a linearization code for the flow characteristics of that one injector. And each injector produced has its a different flow amount, and the flow amounts can be significant from one injector to the rest. So in no longer like a petrol engine that where we can take a brand new 363 Bosch injector or an ID 1000 injector from Injector Dynamics and calibrate that on our bench, and have that within 5% of any injector produced over the next 200,000 injectors that people buy of those petrol injectors. No longer does that become an accurate model for deriving the amount of fuel that you get when we open the injector for a certain amount of time. So now we have a situation where all diesel injectors are different, and we'll do our best to calibrate them and get them in the ballpark for each different model. But as tuners, you need to understand that they are all different. The factory even deals with it. When you change an injector on a factory engine, you scan the barcode here into the factory ECU, and that puts that individual injector calibration into the ECU, and then the ECU itself does ongoing injector calibrations based on cylinder to cylinder speeds. So yeah, there's quite a bit of effort involved in getting injector calibrations even and accurate. So if we as tuners put on an aftermarket ECU and bang in a bit of a guess at an injector calibration and a single injector calibration for all four, we just know for a fact that's not going to be exactly right. Okay, so it's something we have to accept. We're working on a nice calibration method and on a live calibration method to fix that. What we've got right now does work very well, but things like the lambda estimate not lining up with the real lambda are things that can show you that it's not what we think is being delivered to the engine isn't being delivered to the engine. So it doesn't stop you tuning it. You get the same result. When injector calibrations are really bad, you can have trouble getting pilots to phase in and out nicely without affecting power, but it is in the minor drivability stakes rather than the major. So certainly for racing, doesn't affect you as much. It's only really for that lower drivability stuff. So as I said, we're working on it, but this is the purpose of this slide is for you to understand that the issue exists and why, and we've just got to do our best to keep working on it and to get it as nice as we can. Alright, that's a big subject covered. I hope I got most of that through to you. You can keep watching it if you can put up with the voice. And that's it for today, and we'll catch you next time. Thanks for listening.